This is a series of bridges that may not be so easy to cross. Anubhav and Umang are twins who are trying to solve an interesting problem. It involves 7 bridges. Now what we need to do is walk through all 7 bridges without crossing each one more than once. Can they do it? Wondering what all this has to do with maths? Well, this is a classical problem known as the bridges of Konigsberg, and it opened up a whole new area of mathematics. In this episode of Maths Factor, it's all about networks. Through our explorations of this fascinating discipline, we'll learn how to color maps, make travel plans, and understand how we are all connected. Curious? Keep watching to find out more. Back to our twins who are still flummoxed by these bridges and how to cross them without retracing their steps. Now, much like Anubhav and Umang, the citizens of Konigsberg used to spend Sunday afternoons trying to devise a way in which they could walk around the city, crossing each of the 7 bridges only once. Now, where is Konigsberg? Well, it used to be a city in Prussia. It is today known as Kaliningrad and is located in modern-day Russia. Konigsberg was founded in 1254. By the Middle Ages, it had become an important trading center. Some of this can be attributed to its strategic location on the river Pregel. With such a healthy economy, the locals were able to build 7 bridges across the river. Now, as they try and solve this puzzle, there are a couple of rules that Anubhav and Umang will need to stick to. They cannot reach the islands in any other way. They must cross through every bridge. They cannot walk halfway across a bridge, turn around, and later cross the other half from the other side. However, they don't need to start and end at the same point. First off, Anubhav gives it a shot. Not as easy as it looks. Let's pause and take a closer look at Anubhav's route. He's missed a bridge, hasn't he? Could he have completed the circuit if he went on? Nope. He's crossed this bridge before. Can't cross it again, can he? Next up, Umang tries it out. But after attempting it, figures that this is not so simple. He's missed out a bridge too. Well, they don't need to feel so downcast. Even the citizens of Konigsberg were not able to invent a route that would allow them to cross each of the bridges only once. In fact, they were so puzzled that the mayor of Danzig, Karl Eller, wrote to famous Swiss mathematician Leonhard Euler for help. He asked Euler if he could come up with a solution to this problem. In their correspondence, we find this extract. "You would render us a most valuable service, putting us greatly in your debt, most learned sir, if you would send us the solution, which you know well, to the problem of the 7 Konigsberg bridges, together with a proof." But to Euler, who was clearly a busy man, publishing more than 800 papers and books during his lifetime, this seemed like a trivial problem and unconnected to mathematics. In fact, he wrote a letter to Karl Eller. "Thus you see, most noble sir, how this type of solution bears little relationship to mathematics, and I do not understand why you expect a mathematician to produce it rather than anyone else, for the solution is based on reason alone, and its discovery does not depend on any mathematical principle. So Euler wrote off the problem as having little connect with mathematics. And was that the end of our story? Of course not. The idea continued to perplex Euler, and he started playing around with a bunch of ideas. He studied the bridges and he tried to work out a way of reaching an answer. The first conclusion he came to is that the route inside each landmass is not important. He realized that the only thing that mattered was the sequence of bridges crossed. Now, to simplify the problem, he looked at the bridges like this. Let us name each land body. So A lies to the north, B to the south, C is an island, and D is part of the peninsula. So the twins and the citizens of Konigsberg need to cross each of the 7 bridges just once. Now Anubhav and Umang take a shot and see if they can actually go through this network without taking pencil off the paper. With little success, they decide to explore a little further to see if all graphs are as difficult. They wonder if other graphs like these would work differently. The first one keeps quite simple. So does the second. So what was the difference? Now let us look at the graphic representation of one of these networks. There are 6 vertices in this graph: A, B, C, D, E and F. Now a vertex is called odd if it has an odd number of arcs leading to it. Otherwise, it is an even vertex. Could odd and even vertices have any connection with making a circuit without crossing each bridge more than once? It does, because every time you reach a vertex or landmass, you need to leave it by a different route. So an even vertex like A helps. At a vertex like C, you can come and go twice over, since there are 4 arcs. How about at F? You can come and go, but 1 arc remains unused. This could come in useful at either the beginning or the end of a journey, right? Now when we look at the entire graph, A has 2 arcs leading to it, B has 2, C 4, D 2, E 3 and F 3. So here there are exactly 2 odd vertices. So if we start and end on them, we can make a complete circuit. However, if we start on one of the even vertices, we will not complete the circuit. Let's look at the other graph we had looked at earlier and pen down the number of arcs leading to each vertex. A has 4, B 4, C 4, D 4 and E 4. No odd vertices at all, and so it is possible to make a complete circuit without lifting one's pen off the paper. Now back to our original bridges. When we study the graph of the bridges, A has 3 vertices leading to it, B has 3, C has 5 and D has 3. More than 2 odd vertices, and so a circuit is not possible. Now this led to the idea of an Euler path. A graph contains an Euler path if it can be traced in a single sweep without lifting your pencil off the paper. His conclusion was that if a network has 2 or less odd vertices, it has at least 1 Euler path. And so Anubhav and Umang can finally stop trying to cross the bridges. There is really no way around. We have just finished exploring a classical problem called the 7 Bridges of Konigsberg. Now, the significance of this problem, besides being a fascinating mathematical puzzle, is that it laid the foundations for a whole new area of mathematics called graph or network theory. What's the big deal, you may think? Crossing bridges, playing kids' games with pencil and paper? But networks power much of our life today. Which is why Facebook and Google are such powerful companies at creating global connections. Graphs and networks are also immeasurably useful in plotting out shipping and air networks, electricity and water supply networks, delivery of goods, postal services. Our list could go on. Now, I'm going to talk about two other interesting problems that connect with network theory. The answer for one is complex and the other doesn't really have an answer yet. But they both demonstrate the fascinating range of issues that mathematics can cover. Our first problem starts off with an over-enthusiastic Punjabi family who lives in Patiala. There is a wedding in the family and they are planning a nationwide sari shopping trip that will cover Varanasi, Srinagar, Jaipur, Bhubaneswar, Gandhinagar, Kolkata and Chennai. However, the vociferous women in this family are unable to decide which would be the shortest route. Now, can they use network theory to work out a solution? The surprising answer is no. Mathematics has not worked out an algorithm to efficiently solve this problem. They can work out multiple solutions. Broadly, they want to go to 7 cities. They need to start off from Patiala. The first stop could be any of the 7 cities planned. Varanasi or Srinagar or Jaipur or Bhubaneswar or Gandhinagar or Kolkata or Chennai. Now, once you land in the second city, say Varanasi for argument's sake, you have 5 options for the second stop and then 4 for the next and so on. So there are 7 into 6 into 5 into 4 into 3 into 2 into 1, which is 5,040 ways to choose the round-trip route. So our travelers will need to compare 5,040 different routes. Not really efficient, is it? Which is exactly the problem. Now, as the cities increase, so do the options. So if we have 10 cities in the mix, they will need to explore 36,28,800 options. No easy job, which is why we say there is no clear mathematical answer for this problem. Incidentally, this problem is classically called the traveling salesman problem and is one of those problems that sounds very simple and is still immensely hard to figure out. So it's best we leave our battling family and move to our next problem. On to the second problem, which is all about maps. It starts off with a young student called Francis Guthrie, who was a student at University College London in 1852. Now, when we colour a map, it is customary to give different colours to any 2 countries that have a segment of their boundaries in common. Now, Guthrie's theory was that any map on a flat surface, no matter how many countries or states it has, can be coloured with not more than 4 colours in such a way that no 2 adjacent countries have the same colour. The problem, so simply described but so tantalizingly difficult to prove, caught the imagination of many mathematicians at the time. There were many attempts to prove and even to disprove it. Now let's move to an antique map shop belonging to Professor Soni, who is fascinated with this concept. His curiosity is piqued and he has decided to try his hand at seeing how this idea works. He takes a simple image first. How many colors will he need to color this? 4? Not really. You could do it this way with just 2, right? He moves on to a slightly more complicated one. How many colors will he need for this one? 3. Like this. And how about this one? Well, not more than 4. Now let's look at a map. Professor Soni has chosen one with many states bordering one another. And yes, it can be colored with just 4 colors. So is the premise true, or has Professor Soni just not found an exception to the rule? Martin Gardner, editor of the Scientific American, published in his Mathematical Games column this map that supposedly required 5 colors. People were shocked. This seemed to disprove the 4-color conjecture. Well, in reality, this was a joke. The issue came out on April Fool's Day, and this map can be colored using just 4 colors. Finally, in 1976, 2 men called Kenneth Apple and Wolfgang Haken announced that using computers they had managed to produce a proof of this conjecture. The two started off by creating an unavoidable set of 1,936 different configurations, all of which they proved could be colored with 4 or less colors. And then they established that these formed a part of every map. It was the first mathematical theorem to be proved with the help of a computer and aroused much controversy, but at least managed to lay this mathematical ghost to rest. We are today exploring the world of networks that surround us. Networks are nothing but collection of links which combine with specific rules and behavior, almost as if they were alive. How the evolution and concentration of constantly changing connections occurs is the subject of a whole discipline called network theory. Sounds complicated? Do you want to Google it? Well, coincidentally, that's how Google works. Let me try and tell you in a simple fashion. Google sees the internet as a giant graph. Each web page is a node, and 2 pages are joined by an edge if there is a link from one page to another. It's good to realize that the edges in the internet graph have a direction. The algorithm that Google uses to rank its searches is called PageRank. The key idea here is that the more links a page has pointing to it, the more important it is. A second equally important idea is that if an important page links to your page, this is worth more than if an unimportant page links to your page. For example, Wikipedia referencing you is worth more than Little Bo Peep referencing you. So when you search for, say, Ramanujam, the links that surface in Google and the order in which they appear are all determined by PageRank. Now let's move away a little bit and see how network theory can map our lives, our friends, our relationships. Have you heard of 6 degrees of separation? It's a theory that everyone in the world is connected to everyone else through a chain of acquaintances that has not more than 6 links. In 1967, a psychologist called Stanley Milgram tried an interesting experiment to prove this. He selected a group of random people living in the states of Nebraska and Kansas in the American Midwest. He gave them a parcel that needed to reach a stockbroker that they did not know, who lives in Boston. So how would they reach it to him? Each of them would need to send the parcel to someone they knew on a first-name basis. Now, if the recipient knew the intended person, they would send the packet to the final recipient. If not, they would choose a contact they knew on a first-name basis to get the parcel closer to the final recipient. A tracker postcard was also mailed to Milgram so that he could keep tabs on the chain's progression. One would imagine that the chain could go endlessly, but the first parcel reached our stockbroker in 2 hops, and Milgram figured that most people could reach the target in 6 or less links. This idea of Milgram was known as the small world experiment, and truly feels like a small world if the network that connects us to the whole world would have only 6 links. Let's see a tangible example of how this could work. Could we connect Shantabai, a farmer's wife in Bihar, to, say, Bill Gates, the chairman of Microsoft? Now Shanta is a farmer who works in a village in Bihar. Her sister Munni works in Mumbai as a maid. Now Munni's employer, Mrs. Poddar, is an artist. Her neighbor Pradeep loves gardening. Pradeep's son studies in Delhi University. His best friend Ambuja is packing to leave for the US, where she's been offered a job at Microsoft. Bill Gates is the founder of Microsoft. And they all connect with just 6 degrees of separation. Now, many people doubted Milgram's findings, believing that a sample of just 300 was too small, that it was not random enough. In 2001, Duncan Watts, a professor at Columbia University, tried to recreate Milgram's experiment on the internet using an email instead of a package. The findings were very, very consistent with Milgram's. Facebook did the same experiment with a slightly larger sample. 721 million Facebook users, more than 1/10 of the world's population. In 2008, they figured that there were 5.28 hops between any two people in the world. By 2011, this had shortened to 4.7. Which makes us realize that it is a small world after all, if we just stop to think about it. Well, that's about all we have time for in this episode. It has been a fascinating journey to see how networks pervade our life today. The brain is a network of neurons. Organizations are people networks. The global economy is a network of national economies. Food webs, ecosystems, and the internet can all be represented as networks. I think we're networked out for today, but keep watching the Maths Factor for more fun and fascinating forays into the world of maths.